Dear students, in this presentation, we will be discussing two more topics in this module. These topics are polynomials and sparse matrix. Okay, when we solve real world problems, we come across so many different situations. Those kind of problems sometimes are expressed in terms of variables. Okay, we'll be having a kind of expression where it consists varying powers, varying exponent of that variable, which also consists too many different terms. To solve such kind of equations in computing system, first of all, we must be able to store that expression properly in computing system. Without storing that, we cannot solve such kind of equation. First and foremost thing for us is to store it. That expression has to be stored properly. That expression has to be stored efficiently. In this session, in this presentation, we'll be discussing few different ways to represent such kind of expression. We call that as polynomials. What concept can be used? The same polynomials can be represented in different way. As this particular module is pertaining to arrays, we will see how to store polynomial using arrays concept, using structure concept, using array of structure concept. At the end of this presentation, we'll be discussing another form of matrix called sparse matrix. We'll see what is that sparse matrix, how to represent sparse matrix, how to perform few of the operations. Now we'll start with polynomials. Polynomial is an expression of more than two algebraic terms, especially the sum of several terms that contain different powers of same variable. Like if a is a polynomial, a variable that is used in that expression is x. We write a of x in this way. Okay, we'll see that in this slide. Each term of this kind, each term of this format. One is the coefficient, other one is a variable, and this is the exponent. In this expression, we call this as polynomial, having n number of terms, and is finite. 1, 2, 3, 4. Sum of these terms involving a variable x. Here in this first term, the coefficient is 2, a value is 2, x is a variable, and exponent is 3, e value is 3. In the second term, a is 4, a is 2. Here, a is 5, e is 1. Here, a is 3 and e is 0. We don't write that one, we ignore that part because x power 0 is 1. So this is a polynomial. When this kind of expression is given, how to represent that, how to store that in the memory? How can we apply the concept of arrays or the concept of structure to represent this polynomial in the memory? When we represent, we have to consider each terms properly, each term coefficient and exponent properly. When more than one polynomials are given, then we have to store those two polynomials properly, either in case of arrays or in case of structure. Here in this expression, the largest power. largest power. Here it is 3. Largest exponent is called degree. Here we have to note that we have to standardize that polynomials. That is in the decreasing power of decreasing exponents like 3, 2, 1, 0. In the decreasing exponent only we have to store it. Okay, you should not mix. And another point is that this exponent maybe 3 or 2 or 1 or 0 should come in this expression only once. As you can see in this polynomial, all exponents are in the decreasing order. X power 3, x power 2, x power 1, x power 0. So exponent are in the decreasing order, case number 1. Case number 2, only one, that is exponent 3 in this expression, only one term. You should not have another one. If another one is there, you have to find out the final expression, because purpose of this is to store that polynomial properly in our memory, in the computer memory. So only one term of power 3, only one term of power 2, only one term of power 1, only one term of power 0. Okay, these are the two things that you should note. The degree of the polynomial is highest power, okay, and all the exponent are in the decreasing order, and only one occurrence of that exponent in the expression. We'll take some example. Let A and B are the two polynomials. We can perform addition, we can multiply, we can find out whether that is a polynomial or not. Then we have got some operation like what is the degree of the polynomial, or we can also use function to retrieve the coefficient of that highest exponent or coefficient of any term. So these are the different operations that we can perform. So once again, we can multiply a number to a polynomial, we can multiply two polynomials, we can perform addition on two polynomial, we can test whether polynomial is having some terms or not, like that. We'll see all those lightly in this presentation. Now, we can write these functions in any of the language. These are all not exactly the function. Programmer point of view, you can write a program. We can write a program for all the things. We call that as ADT, abstract data types. The functions are, abstract data type functions are, one is zero function, which returns a polynomial having no terms, which returns a polynomial. Zero means is a function named 0 which returns a polynomial, without any terms. Suppose A is the polynomial that I need. I don't want any term. I can call 0. A equal to 0 means A of x becomes 0, because a polynomial is created but without any terms. The second ADT is 0. This function is to test whether that polynomial is having terms or not. If there is no term at all in the polynomial, should return true, should return 0 or true, otherwise false. As we have created a polynomial A, if we pass A to is 0, A is having no terms. So it is a polynomial with 0 terms. So answer true is returned, returns 0. Okay. If we pass this polynomial b of x, is it a 0? We have got a term. It is having one term, 6x. So it returns false. If we pass b of x to this function ADT, returns false, because it is a polynomial with one term. Next, the third ADT. For all these you can write C program or any other language programs. These are all general functions or operation that we can perform on polynomial. Next, which returns a information called coefficient. In the polynomial we have got two information. One is that coefficient, other one is that exponent, this one, 2 here, 0 here, coefficient 8 here, 2 here, that is the coefficient. Now I want to know coefficient of one of the term, coefficient of one of the term. For that I can use COEF. It is a general function ADT COEF which returns a coefficient. So for that what you have to supply, one is the polynomial, other one is the exponent. Now, COEFF is a function name. I'm passing A. This one, this is passed. Here afterwards, you consider A of x, and exponent 2 is passed. This one. What is the coefficient of the term which is having exponent 2? The coefficient is 8. As you can see here, 8x square. 8x square, what is the coefficient? Coefficient is 8. So this function returns a coefficient value 8. To get that, no, you have to pass one polynomial and that exponent. Suppose you pass 1. Do you have any coefficient here? We don't have x term, so answer will be 0. If we pass 0, the answer is 2, like that. Okay, the polynomial name and that exponent, these are the two things to be passed to this function. The last, I want to get the degree of the polynomial. In this case you can see 2 is the highest power, that is the degree of the polynomial. If we pass A, 2 must be the result. If we pass B, 1 must be the result. To get the degree you can use lead exponent, leading term, the first exponent, that is the answer, the first exponent. Okay, here lead exp of A, if I pass A to this lead function, what is the highest degree? Highest degree is 2. If you pass B, then highest degree is 1. Okay, then attach. What to attach? A term to attach. Term has got coefficient and exponent, that has to be attached to a polynomial. Okay, so that returns the resultant polynomial. I'm performing some kind of attachment, joining one new term to the existing one. We'll see what happens. I want to join one term to A. What is that term? 3x. 3 is the coefficient, 1 is the exponent. 3 is coefficient, 1 is exponent. 3 is coefficient, 1 is exponent. To what? To A. What is A? 8x square plus 2. 8x square plus 2. What to attach? 3x is attached. When you are writing, you have to see that all the exponent are in the decreasing order. 3, 2, 1, 0, like that. Here 2, 1, 0. Okay, this is a point to note. C is the final answer. C equal to 8x square plus 3x, that is attached, plus 2 old one. Okay. Now I don't want one particular term in the polynomial. I want to remove a term. For that I can create a function. I can call remove function, where we are passing a polynomial and which term you want to remove. You have to specify the exponent. Exponent is unique, not the coefficient. We can have all exponent coefficients same, but exponents are different and unique. Now what I'm doing, I'm going to remove a term whose exponent is 2 from C. This is my polynomial. Well, you can refer this one, C. If I pass C and specifying that exponent value 2, that means this term will be removed. This term will be removed. That is the final result. D equal to, after removing this term, 8x square is removed. So remaining answer is, remaining terms are 3x plus 2. 3x plus 2 after removing exponent 2. Now I want to multiply something to the polynomial. What to multiply? A term. Term is consisting coefficient and exponent. To the polynomial I have to multiply. The end result is again polynomial. We'll see what happens. I'm going to multiply 2x power 1 to d. This is my d. I'm going to multiply 2x power 1. 2x into 3x. 3 into 2, 6. X into x square. So 6x square. 2x into 2. 2 into 2 is 4. Then x. That is multiplying one term to the polynomial. That is about multiplying a term to the polynomial. Now we'll add two polynomials. When you perform addition, the result is again a polynomial. We'll see what happens. My two polynomials are d and e. D is 3x plus 2, E is 6x square plus x. Only the corresponding terms you have to add. 6x square or x square is not here in D. So nothing is added. That means 0 is added. 6 plus 0, that is 6. The term x square. Okay. You can also write by keeping all the terms with the exponent 0. If you don't have x square, no, you can write 0. 0 plus 6 x square. Now 4x is here and exponent x is also here. 4 plus 3 is 7x. 2 plus 0, I can write like this also. 2 plus 0 is 2. This is about addition. The result is again a polynomial. This returns polynomial. Last one in this, that is polynomial multiplication. Two polynomials are multiplied. Result is again a polynomial. What is all multiplied? A and B are multiplied. A is 8x square plus 2. B is 6x. 8 into 6, 48. X into x square, x cube plus 2 into 6, 12. X, 12x. This is the result after multiplying two polynomials. The result is again a polynomial. These are different ADTs. Now, the question is how to represent that. How to represent. Now we'll make use of structure. As you know that there is a highest degree. One term that we use in the polynomial is the degree of the polynomial. Based on the degree, we can reserve that many number of spaces. That many number of spaces. The other one is coefficient. Coefficient. Then the degree. Coefficient and that degree. If the term is not there, you put 0. The thing is, uh, we can have any number of polynomials. So for that you have to create the array. Okay. Now I will take this example. See what happens. Okay. What is my first polynomial? 100. Oh, sorry, 2x to the power 100 plus 1. Okay. Now how many spaces I have to reserve? If this is my polynomial to store, this is my array to store the polynomial. First I have to store the degree. What is the degree of this polynomial? Degree of the polynomial is 100. Then the coefficient of all the things. The coefficient of highest, that is 100. 100 is 2. Coefficient of 100 is 2. Okay, don't refer this one, this you refer. Next, coefficient of 99, 0. Coefficient of 98, 0. 97, 0. The problem is actually we are wasting the memory. This is the worst case example. After this, we go for the next polynomial. This much space you have to reserve. The finally here we get one. All these are 0. All these are 0 because we don't have any terms of that exponent. All these are 0. It is a waste. That this particular method is wasting the memory. Next, after this, now we are going to store the next polynomial. What is the highest degree? 4. That many locations are created. That many number of locations are created. Highest degree 4. What is the exponent of that? 1. Next is 3. What is the exponent? 10. What is the next one? 2. Exponent 2, coefficient 3. Next, x is not there, 0. The last one, 1. This is the thing. In this method, there is a wastage. There is a wastage. These many locations are simply wasted. So it is not worth one to store to follow this for representation. Then, do you have any other methods? With a small alteration, we can store this polynomial. So that is the second representation. Just by making use of coefficient and exponent. Just go on store all the things, but you keep 4 pointers. The 4 pointers are what is the beginning of the polynomial, what is the end of the polynomial, what is the beginning and what is the end. These are the terms required. If there are 6 terms, then we should have 12 pointers. If there is only one polynomial, then 2 pointers are required. In this case, same example take. 2 polynomials are given. For each 2 pointers, 2 into 2, 4 pointers required. We are representing the first polynomial. The start date that indicates the beginning of that particular polynomial. What is the coefficient? 2. What is the exponent? 100. Do you have any more term? Yes. What is that term? Coefficient is 1. Exponent is 0. Do you have any more term? No. That means this is the end of the first polynomial. End of the first polynomial. In the next location, start storing the next polynomial. What is the next polynomial? B. Start storing. That is the starting point of polynomial 2. What is the first term? X. 4. What is the coefficient? 1. Altogether 1. 4. Do you have any more term? Yes. What is the exponent? 3. What is the coefficient? 10. Do you have any more term? Yes, repeat. 3 is coefficient, 2 is exponent. Do you have any more term? Yes. 1, 0. Do you have any more term? No. You point that with the finish pointer. Okay. This is the second representation. First representation wastes memory location. Second one is more efficient one where we don't find any wastage of memory locations. So we follow one of the representation in this way. In case of array, go on store, but you keep track of each of the column with the pointers, starting pointer and finishing pointer. If there are n number of terms, at least you should have 2 into n number of pointers. Okay, that is about polynomial. We'll see some more ideas like polynomial multiplication in the second module and the third module. Okay, this is just introduction on polynomial. Next is sparse matrix. We know what is regular matrix. Regular matrix is a arrangement of all the values in row wise or in column wise. This 2 cross 3 indicates that these values are stored in 2 different rows and 3 different columns. Okay, any of the element can be retrieved with the index. In this case, if array name is A of I comma j means you are accessing ith row, jth column element. So when you are storing, you have to see that this is the maximum permitted row, maximum permitted column. Okay, so at the most, if 10 is given for max row, 10 is given for the max column, 100 by 10 by 10, 100 into word size locations are result. That is in case of regular matrix. There is another special type of matrix called a sparse matrix. See, when we deploy a number of sensors for different purposes, we take data from those sensors. Okay, like these are the samples values. Just an example only. These are the values from each of the sensors pertaining to one of the detail. These are all the details. One type of pressure, all those things, pressure or temperature or humidity, like that. So these are the things. If the value is sensed, that value will appear in that particular row and that particular column. And when the value is not sensed by the sensor, we put to 0. Okay, as you can see here, there are 6 samples. 1, 2, 3, 4, 5. These are the 5 samples pertaining to 6 different attributes. These are all attribute. 1, 2, 3, 4, 5, 6. 6 attribute on 5 different samples. You can see here there are too many number of zeros. Too many number of zeros, but very less number of non-zero values. A matrix which consists too many number of zeros and very less number of non-zero values. That kind of special matrix is called sparse matrix. Sparse matrix is a special type of matrix which contains too many number of zeros entries, too many number of rows or columns or the cell having zero values. Sparse matrix or a sparse array is a matrix in which most of the elements are zero, very less number of non-zero elements. If the most number of elements are there, it is not worth to store all the things. Suppose this is the array to be stored. Why you have to waste the memory to store zeros? Correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 cells you have to waste to store zeros. Very less 1, 2, 3, 4, 5, 6 non-zero values. That is okay. But what is the use of storing zeros in the memory? So we have to find out some alternate method to store only non-zero values. Okay, that we are going to discuss how to represent that sparse matrix in memory. Okay, with the help of arrays or structures like that. In reality, if there are 2000 cross 2000 matrix, hardly we find 100 or 1000 values out of 4 lakhs entries. If we make use of our ordinary array concept, these many number of locations you have to reserve. But actually, we are replacing very few number of locations for non-zero values. That is a simply wastage of memory locations. Okay, because computer memory is a costlier one. We should not waste for unnecessary things, for storing unnecessary information. So, which leads to wastage of memory locations. Now we'll see how to store that one. We follow this kind of triplet format, triplets that will indicate where is that values, in which row and in which column. Before that, we have to specify how many rows, that maximum number of rows, how many columns, that the maximum number of columns, how many non-zero values, that is in the first row. You can see here. I'll come back to that slide later. If this is a matrix, if this is a sparse matrix, this is a sparse matrix. Okay. Here we have to have a triplet representation. This is a representation important. Triplet representation. It is having 3 information. One is row, other one is a column, the last one is the value. Okay. In this sparse matrix, how many rows are there? 1, 2, 3, 4, 5 number of rows. The first row is that information which will hold number of rows, number of columns, number of non-zero values. 5 rows in this matrix. Number of columns in this matrix: 1, 2, 3, 4, 5, 6. This is the number of columns, max columns. This will give the size of size matrix, sparse matrix. The last one, number of non-zero values. Count the number of non-zero values. 1, 2, 3, 4, 5, 6. There are 6 non-zero values. See, if this representation is not there, actually we have to allocate 5 into 6, 30 into 4 cells. 30 into 4. 30 into 4, 120 memory locations you have to allocate it for this array. That can be reduced with this arrangement. Okay, now go on trace this matrix. Where is the first non-zero element? Which row? Zeroth row. Which column? 0, 1, 2, 3, 4. What is that non-zero value? 9. The next non-zero value is 8. What is the location of that? Row number 1, column number 1. Row number 1, column number 1. The next value here in the third row, that is index 2. Row index is 2. First column index is 0. Value is 4. The next non-zero value is 2. 2. Where? In the same row. Second row, second column, second row, third column. Okay. 0, 1, 2, 3. Here 3. 3. Okay. 3. This is 3. Next. Here. Third row. 0, 1, 2, 3. Third row. Which column? Fifth column. What is the non-zero value? 5. Next. Last row. 4, 2. 4, 2. The non-zero value is 2. This representation is more efficient one because we don't find too much of memory location to store zeros. We don't find any non-zero values here. All are, sorry, we don't find too many zero values here. All these are non-zero values. We don't waste memory for storing zeros. Okay, this is more efficient one. As you can see, three informations are required. This is a structure. If you consider this as a structure, this is one particular row having three information. One is row, other one is column, last one is value. So in the same way, we create a structure for sparse matrix. Structure name with first information as row, column, and value. We can have any number of terms up to max. How many number of non-zero values are there? That many number of rows you can reserve. Okay. What are the different operations we can perform? The first operation is creating that sparse matrix. This will allocate memory. How many rows? How many columns? These many number of rows. These many number of columns are created. An empty sparse matrix is created, which will hold up to these many entries, max row into max column entries. Second operation is transpose. You know how to transpose a matrix. The same we can also transpose sparse matrix. The value of row and column get exchanged or interchanged. The last one is addition of two sparse matrix. Addition. Two sparse matrix if A and B are so, then A and B will be multiplied. A and B are added. So only if dimensions are proper. Otherwise, it's not possible to perform addition. The last one, as you know, is multiplication. The row of column of the first matrix and the row of the second matrix is same, then only you can multiply. Otherwise, it is not possible. That basic rule is same, but how to perform that is little different because we don't have zero values. We are not representing cell with zero values. We have to play with non-zero values only. Okay, slight change in the algorithm. We'll see those algorithms now. Okay, let us take one more example. This is my matrix. This is a triplet form. Okay, the structure name term. Structure name is term. Term dot col. The first number of columns, number of rows, number of columns, number of rows values are stored. Can see the first one, number of rows 1 2 3 4 5 6, number of columns 1 2 3 4 5 6, number of non-zero values 1 2 3 4 5 6 7 8. The first non-zero values at 0 comma 0. First non-zero value is 15. Second non-zero value 0th row, third column, that is 22. Next non-zero values minus 15, where same row, fifth column. Next non-zero value, first row, column 1, value 11. In the same row, we have got one more, that is 3. 1, 2. In the next row, value is minus 6, 2, 3. Next, 91, 91. Fourth row, index is 4, 0, 1, 2, 3, 4, 4. Column is 0. The next non-zero value in the last row, row number 5, column number 2, value is 22. This is the representation which uses three information, row, column and value. Row, column and value. That representation is triplet representation. Okay. You know that transpose where we are interchanging row value to column value. Okay. If B is my resultant matrix, B is my resultant matrix, A is the original matrix. I have to transpose A, which produces B. How to transpose that one? So in this case, we have to repeat that for these many number of columns. In this matrix, there are 6 columns. You have to repeat 6 times. In each time, you have to see column for 0. You have to start scanning from the first row till the last. Then you have to scan column 1 from here to here. Next you have to scan for 2, column number 2. Next you have to scan column 3. Next 4, next 5, like that. Okay. Thing is that here this will waste our time. That many number of times you have to repeat. 6 into 8, 48 times this has to be repeated. Sometimes it is success with success, sometimes without success. We'll see now. I value start from 0. How many number of columns are there? 6. That means I has to be repeated from 6 to 0 to 6 times. 0, column 0, column 1, column 2, column 3, column 4, column 5. Total 6 times you have to repeat. Right now we are scanning for column number 0. So j value start from 0 till number of terms. Here number of terms are 8. 8 times you have to repeat. Okay. Next, a of 0 dot column. What is that value? 0. Is it matching with the I? I value is also 0. They are matching. Now what to do? You interchange. Row will become column in B. Column of A will become row of B. Value will be copied. Value will be copied. Okay. These two. This is I. A of now this 0, 0 are same, that will be copied here. 0, 0, row 0 will become column, the value will be same. That is after the first one. Next, like that, you have to repeat 8 times. Go for the next row. Go for the next row. The next row, this one 0 3 2. What is the column value? 3. Is it equal to 0? No, skip. 5. Is it equal to 0? No, skip. 1. Is it 0? No, skip. 2. Is it 0? Skip. 3. Is it 0? No, skip. 0, which is equal to I value 0. Now where to keep this one? So this will come in the second. So column will become row, row will become column. This is row value that becomes column. This is column value that become row, and value same. Value same. See, simply we have wasted this much of time. Correct. Next, the last one again wasted. That is about I equal to 0. Next, for I equal to 1, again you have to start scanning from here. 1. Not a true, not a true, not a true, true. So that will come here. Okay. 1, 1, 11. Not matching to 1. No match, no match, no match. 1 is over. Go for the next value of I. I value is now 2. Again, you start from here. Not matching, not matching, not matching, not matching, it's matching. 1, 2, 3 become 1, 2 become 2, 1. Sorry, more was here 2, 5. Okay, anyway, 2, 5, 28, 2, 1, 28. Interchange, anyway, that is okay. 2, 1, 3 and 2, 5, 28. The next value is 3. 3. Not matching. Column of A matching that with A, I value 3. Column value of A is matching that with I value, that is 3. So 3 0 3 22 will become 3 0 22. 3 0 22. Next, where we got another column with 3. This is the 3 is matching that with I. Okay, 3 to 6, 3 to 6. Next, we don't have any more threes. Next, we'll go for the next I value 4. Again, you have to waste 8 times because we don't have column 4. That is wasted, 8 time wasted. Then last one 5, waste, waste 5, 0, 5, 15 becomes 5, 0, 15. Even though all values are over, but no choice, you have to complete it till the end. So this is the wastage of time. See, here there are I varies from 0 to 5. That means total 6. In each time you have to repeat these many number of rows. 1, 2, 3, 4, 5, 6, 7, 8 times. 48 times you have to repeat. Okay. So at the end now, actually how many rows are there? 8 rows. Successful is only 8. 48 minus 8. 40 iterations simply wasted. 40 iterations simply wasted. So this is not the best algorithm to use for transposing sparse matrix because we found too much of wastage of iterations or computation time. Then another method is there that is name itself tells fast transpose compared to ordinary transpose. This will reduce the time. Remember that 48 in the previous case, no, we got 48, 48, 48 total iterations, 48 total number of iterations. Note down here 48. In that only 8 useful, 40 simply wasted. Now this algorithm goes like this. We have to make use of an array. We call that as row terms. That will count that particular row count in the array. Okay, we'll come to know when I start tracing that one. Purpose of this is to scan all the row. Okay, after scanning all the row, now we'll come to know number of occurrence of each of the column. Number of occurrence of each of the column. I'll explain that in the next slide. Next, in the next, you have to find out starting index. Where to place that particular column in the matrix. Okay, by knowing that starting index, go on place that element from that sparse matrix in the proper place. Anyway, I'll start tracing that algorithm now. Okay. Now here, how many row terms are there? How many rows are in this matrix? There are 6 rows. I have to initialize all 6 rows to 0. Initially all 6 row terms of 0, row terms of 1, 2, 3, 4, 5 are all initialized to 0. This is the first step. That is the first step. It is given here. Initialize row terms to 0. This one. Initialize row terms to 0. That is the first step. The second step is that start tracing these sparse matrix rows. Now we are in the first row. Okay, right now we are here. What is the column value? Column value is 0. Why this name is given? Because this row will become column here. This column will become row here. Okay, that is why number of row terms. At the end, we will be having 2 rows. These columns, 0th column, 0th column, that becomes number of rows in the resultant matrix. Like that, 3 becomes number of rows for 3, 2. 1, only 1, you can see only 1 row count. No number of row terms of that index 1. We don't have any 4, 0. Number of fives, only 1. Only 1, this one. For that purpose, we have to initialize the array. Row term that doesn't indicate this one, this actually number of these values, column values. Okay, we start tracing. Right now we are in the first row. Right now we are in the first row. Row terms, whenever the column value is matching that with the index 0, increase it. We have reserved 5 arrays: row of 0, row of 1, row of 2, row of 3, row of 4, and row of 5. 5 arrays we have reserved. Okay, what is the index value? 0. Corresponding row terms you have to increase it. What is the corresponding column value? Is 0. Out of these 5 we have to take this array, row terms of 0. Earlier value was 0, increase it by 1, that becomes 1. That becomes 1. What is the next one? Column value is 3, the index value is 3. Search for that particular array, row terms of 3. The value was 0. 3, 0 plus 1, that is 1. What is the next one? 5. Search for the corresponding row term array, value is 0. 0 plus 1, value is 1. Next one, row term of 1. Row term of 1, whether we updated or not yet updated, so 0 plus 1. 2. Row term of 2. Row term of 0 plus 1, 2. Now the value is 3. Value is 3. Value is 3. Do you have whether we updated that? Yes. Don't take this value. Already we updated in that memory. That 0 will be replaced by 1. This value is 1. 1 plus 1 more, 2. 1 plus 1, 2. Okay. We don't have 4 at the end, also that 4 only. Then what about 5? 5 is here. Increment. The last one, 2. 2. What is the updated value? 1. Add 1. 4. That is given in the algorithm here. Okay. You have to increase. First you have to initialize row terms to 0. Okay. The next is finding out that particular column index, that becomes row terms. After add it, update it in the memory as explained in the slide. The next step is again you start scanning. Okay, this is to fix that particular in the array. Okay, starting position, to find out the starting position. You assume that starting position of 0 is 0 initially. I'm sorry, starting position is 1. Why 1? Because at the end also this value is retained. The index of this is 0. In the array the index is 0. Our elements can be stored only from the index 1. That is why starting position 1. This is for this value, where that value has to be placed. 1, 2, 3, 4, 5, 6, 7, 8. Now we will see starting position for 0. How many 0 columns are there? 1, 2. You have to start from 1. Then how many 0 columns? 1, 2. So you have to resolve 2. 2. Okay. That means the column number 1 must be placed after skipping these 2 rows. For that, starting position of 1 is the row, the count plus 2. Starting position 1 plus value. What is that value? Row terms of 0. Okay. This is obtained by, this is, we will take the starting position of I, that is equal to starting position of I minus 1, value is 1, plus row count of 0, row count of I minus 1. Row count of I minus 1 is 2. 1 plus 2 equal to 3. So that means we have to skip 2 rows, then we are going to store the column with value 1. Okay. Now, in the original matrix, how many rows are there with column 1? Only 1. That means you have to skip only 1 row. So second index starts in the next place. How to get that one? Starting position for the second column is starting position of 1, the previous one, plus row terms of 3. What is the row terms of 1? 1. Starting position of 1, 3. 3 plus 1 is 4. That means the index 2 will start in the row 4. 1, 2, 3, 4. Okay. Now, how many columns with the 2? How many number of things are there with column 2? 1 here, 1 here, 2. That means you have to skip these 2 for the next index. The next index can be stored after skipping 2. Okay. How to get that in the formula? Starting position for 3 is starting position of 2 plus row terms of 2. Starting position of 2 is 4 plus row count of 2, that is 2. 4 plus 2 is 6. After skipping 2, 4, 5, the 6 is the starting place for 3. Here in the original matrix, how many columns with the 3? 1, 2. That means you have to skip 2 more. That can be obtained with this formula. Okay. If there is a column with 4, where to put it? That is given by this formula. Starting position of 4 equal to starting position of 3 plus row count of 3, 2. 6 plus 2 is 8. If there, that should come in the 8. Unfortunately, that 4 is not there. Means 0 row to be skipped. Column with 5. Okay. How to obtain it? Starting position of 5 is starting position of 4 plus row terms of 4. Starting position 8 plus row count is 0. We don't have that here, that is 0 only. So 8 plus 0 is 8. Okay, so this is the thing. Next, again you start tracing it. The first one is 0, 0, 15. Where to place it? As it is the first one, that will come in the first index only. 1, 1. So you, by interchanging that row and column, 0, 0, 15, I'll clear that first. Okay. So the first value is 0, 0, 15. Where to keep that one? In the first row. Interchange row and column. Place the value. Then you have to increase this value. Starting position of 0 you have to increase. Now it is 1. You have to change that value to 2. Be ready to put next column 0. Okay. What is the next one? 3. Column value is 3. Interchange that value. That becomes 3, 0. 22. Where to put that one? Go to this array. Search for starting position of 3. You put that value here. As you put, increase this by 1. 6 plus 1. Here afterwards, if you want starting position of 3, refer this value, updated value. Here you refer this value, updated value. Okay, what is the next one? 5. Go to this array. Which index you have to refer? 5. You have to refer 5. Where to put it? 8th row. Interchange that value 5, 0. If there you increase it, okay, let it be 8 plus 1, 9. Okay, what is our next value? 1, 1, 11. Search for 1. Index is 3. 1, 1, 11. As you already added one value, increase it. 3, 1. The next value is 1, 2, 3. Go to this 2. Value of that is 4. Interchange the value. What is that value? 2. Okay, 2, 5, 1, 28. Interchange 2, 1, 3 actually. Okay, 2, 1, 3. Next, increase that value. Let it be. Next value is 3. 3. What was there? 7. Go to that 7th row. Go to 7. 7 means this one. 7 means this one. 1, 2, 3, 4, 5, 6, 7 here. Put that value. Oh, what is that value? 3 to 6. 3 to 6. Increase that one. 8. If there, will come here. Next, 4, 0, 21. Go to 0. 0 already there. 2. Go to here. See. Exactly in the place the value is put. Value is 0, 4, 91. Last one, 2. Whether we updated? Yes. 4 plus 1, 5. The fifth row you have to refer 1, 2, 3, 4, 5. In the fifth row, what value you have to put? 2, 5, 20 you have to put. Actually, these two values are interchanged. 2, 5, 28 you have to put. This is how the sparse matrix done. You can see in the program. The last phase is given here. Okay, just trace this in your free time. Now I'll be computing number of times required. Number of columns in that example 6. That means this is repeated 6 number of times. 1 to number of terms. There are 8 terms, so 8 times this is repeated. We'll see. Our main purpose is to save the time. Okay. Number of columns. This is repeated 6 number of times. This is repeated 8 number of times. Add all together. 6 plus 8, 6 plus 8, 28 times. In that case, it was 48, which is good one. 48 or 28? 28. In this many number of times repeated, here 48 number of times. In this case, it is just 28 times. So fast matrix, that is why it is called fast matrix, because compared to the ordinary transpose, no, this saves time. Okay, this is about sparse matrix. Thank you for listening.